Hi everybody, this is going to be on section 3.4. That's the last section in chapter 3. So upcoming stuff, we begin chapter 4 with the next lecture, and that's where we start to do mathematical proofs, which many people find is the most challenging part of the class, but it's a good sort of challenging, like it's the sort of thing you really stretch your mind with, so look forward to that. This section is probably going to go really quickly because we've previously talked about arguments, and the only difference now is that we're going to be doing them with statements that are quantified. So it's more or less a repeat of the argument forms with quantifiers added in. Well, the very first thing in this section is an interesting little rule of logic, of argumentation really. It's called universal instantiation. Just write it all out for you. Universal instantiation. And what that means is if you know something is true for all the elements of some set, and then you pick out a particular element of the set, well, the thing is going to be true about that particular thing. So you might have something like, sorry, that's funny, I started to use the symbol for all, but I want to say something like, all professors at Southern are awesome. And then if you pick a particular professor at SCSU, then you get that they're awesome. So like me, Dr. Joe is awesome. You do need to have a true thing, a true universal sentence before you can conclude a true particular case of it. But in any case, that's called universal instantiation. If you've got something that's generically true, then it'll be specifically true for individuals. Remember the argument we did, all men are mortal, Socrates is a man, therefore Socrates is mortal? That's really a universal instantiation. We were saying all men, well, instead of awesome, are mortal. And then Socrates was mortal. I'm not comparing myself to Socrates, but you get the idea. So let's look at the two argument forms we did last time, and then we will add quantification to the mix there. Remember the modus ponens argument form? It looked like, well, let me remind you of it. Modus ponens was the one that looked like P implies Q, P therefore Q. It had this shape to it. And the change when we go to a universal form is mostly in the major premise, but it's also in the sentences, P and Q. These now need to be open sentences with variables in them so that quantifiers make sense. Right? So let me just redo it. If I have P of X and Q of X, also remember the if-then arrow turns into this double wide arrow now. Excuse me. And this sentence needs a quantifier. So the universal version of modus ponens quantifies it as for all x. P of x implies Q of x. Now, there's two variants, and I'll give you the first one first. You'll then have P for some particular element of the universe. Not x, which is ranging over everything, but some particular guy, P. And what will you conclude from that stuff? Everything, if P is true of it, out of all things in this universe, if P is true, it forces Q to be true. And we know that P is true for this particular thing. Yeah, well, Q is going to be true for that particular thing too. So what we've just created there is a version of modus ponens that's called the universal version, but there's a subpart to it because we did a particular thing as the minor premise and as the conclusion. So that means what we've got here is the particular form of universal modus ponens. I'm just going to abbreviate that to MP because I think we know modus ponens. I don't have room. So there is another version of this, which is universal and universal. You can have the universal form of universal modus ponens. How would that change things? Both the P of X and the Q of X here would be universal sentences. I think I have no choice but to erase something and do a new section of the board here. So if you had, it's always true in our universe that P of X implies Q of X. And it's always true in our universe that P of X is true. From that, you will conclude that it's always going to be the case that Q of X is true. I've just noticed I'm falling into a shorthand that I sometimes do, which is to think that the universe of discourse where we're doing this argument in is sort of understood. It's just in the background. If you don't like that, and some people don't, these for all x's should really be for all x's in U. You should really write something like for all x in the universe. Q of X, and all of them the same way. You should really specify the universe. But a lot of times, what I've done here as a shorthand is the way people really work, which is, the universe is understood. Maybe we're working within the set of rational numbers. So I know that anytime I write for all x, I really mean for all x in Q. Okay, I gotta also label this with its fancy name. And this one is the universal form of universal modus ponens. Now, I'll be honest, this kind of argument happens occasionally, but it's rare. This is much the more common form. You're trying to use that the implication is universally true to get that Q is true for some particular thing. So you need to show that P is true for that particular thing, and that'll do the job. This is much stronger, right? Okay, you might be able to show that for all x, the P implies Q, but then making sure that the P is true all the time, well, the sentences P that are true all the time are a little bit rarer than the ones that are true just for some particular guy. So this is what's known as stronger hypotheses. In particular, the minor premise there is a stronger premise. So it's a harder argument to use because you just have to have more ammo before you can make it fly. So let's do an example of an argument that's of that shape, that has the universal modus ponens things. How about this? Every odd number has a square that is also odd. Seven is odd. Therefore, well, maybe I'll stop for a second and ask, what do you think you would conclude? 7 squared should be odd. I'll just put that in parenthetically, perhaps, because we don't really need to know what 7 squared is. I mean, it's cool that it checks, though. When you square 7, you get an odd number, but the idea is to sort of deduce that 7 squared is odd without having to figure out what it is. It's not hard to square 7, but if this was 1,000,001, well, actually that wouldn't be that hard either, but you get the point. You don't want to be doing calculation, you just want to know if it's true that every odd number has an odd square, and you've got a particular odd number, you know the square is odd, without having to necessarily do that. Now, does that actually look like modus ponens to you guys? Probably not. So let me make sure we can rephrase this so that it looks like modus ponens. It should look like an if something implies a then something. How do you rephrase every odd number has an odd square? Well, I'd say something for all x in the natural numbers, perhaps. This universe could be different, but I'm using natural numbers. If x is odd, then x squared is odd. Now does it look like well, first of all, do you agree that has the same meaning? Every odd number has an odd square. For all x in the naturals, if x is odd, then x squared is odd. I hope just informally that makes sense that those are identical. Then we've got 7 is odd. Sorry, 7 is odd. And we conclude 7 squared is odd. These didn't really change. And that's nice because that lets you spot what the predicates are, what are the variables. If this one's supposed to be P implies Q, this one's supposed to be P of some particular thing. So what I'm looking at right there is P of 7. And what I'm looking at on the bottom line, on the conclusion, is is Q of 7. So what are P and Q in particular, or P of x? P of x is about oddness for x. And Q of x is about oddness for x squared. You see how we're able to identify the predicates? So yeah, it fits the form, right? We've got a if-then involving P of x and Q of x. It's got a universal quantifier up front, and then a particular version of P at the value of 7, happens to be true, and then concluding Q at the value of 7. That one's slightly weird because you could see that this Q is really P applied to 7 squared, but maybe if I said it again informally, the number is odd and the square of the number is odd. Those are really different ideas. Let's look at modus tollens, since we've seen it before, but how will that change? Again, you'll have a universal form and a particular form. I think I'll just do the particular form because, again, the universal versions, the doubly universal ones are a bit rare. So let's look at the particular form of universal modus tollens. I feel like my marker's getting a little gray here, so I'm going to trade out for a better, darker one. Particular form of, is that better? I hope it is. Universal modus tollens. I'm not quite sure why I capitalized the M and the T in there. They're not normally done that way. That's probably because I've been taking German lessons, and in German all the nouns have to be capitalized. Sorry. So let's just make these lowercase, and it won't seem so weird. Particular form of universal modus tollens. So while it starts the same way universal modus ponens does, your major premise is for all x. Okay. I'm not going to make that same mistake twice. We should refer to the universal set. So this should be for all x in the universe. P of x implies Q of x. Major difference between what we did before and what we're doing now is these are open sentences, and we've got the doubled version of the implication arrow. The next one is going to be some particular value has the negation of Q true for it. So it's not Q is true for some particular thing. I think P is fine for that. And then we conclude not P for that particular guy. Trying to see if they have a good example in the textbook for this. Yeah, I'm not going to go with that one. I've got a silly one. All right, well, here's an argument I just made up on the spot. It's probably a stupid one, but I just wanted to have a quick example of it. All people who like black jelly beans are strange. I'm not strange, therefore I don't like black jelly beans. Let's see if we can identify what are the premises, what are the predicates that are used in this thing. First off, it's clearly universal, and I think the conclusion of this thing, if you see it as an if-then, is relatively quick. It's just strangeness, right? So that's your Q of x. X is strange. The other part is a little longer. All who like black jelly beans. So that's what I would call P of x. It's this little bit about, maybe it's even that, people who like black jelly beans. All right, but that's P of x, where x is the people, you know, the unspecified people. But all right, so we're saying for all x, if x is someone who likes black jelly beans, then x is strange. All right. So yeah, we've got a for all x, P of x implies Q of x up front. That's again, the major premise is that one that involves an implication. What do we got on the second line? It's actually the negation of Q of x for whoever the speaker is here. So that's not Q of I. I guess it's me, because I'm the one who wrote this thing. And what is the conclusion? I don't like black jelly beans. That's the liking of black jelly beans sentence about the speaker, person I. It's got the modus ponens shape, and it's got particular things in the minor premise and in the conclusion, where it's the major premise is universally quantified. So that's what I claimed it was going to be, the particular form of universal modus tollens. I think, playing that back in my head, I think I said it had the modus ponens shape, but it does not. This is the modus tollens, the method of denial, the negation of the then piece is your minor premise. Okay, so there's a little spiel in the back of this section about a guy named Gottfried Wilhelm von Leibniz, who is arguably one of the greatest philosophers and mathematicians of the 17th century. Well, he was born in the 17th century. I always get that century bit mixed up. Most of his work was in the 1700s, though. So that's 18th? Leibniz was one of two people who independently discovered calculus. The other one is somewhat more famous. Newton, Isaac Newton, also discovered universal gravitation and a few other things. Newton, weirdly, he discovered calculus and he decided not to tell anybody because he felt like he had this magic arsenal for solving problems, and he could there was, at that time, people would often throw out like contest problems, challenge other people to solve this thing. Well, Newton had this ace in the hole, as it were, that he could solve all kinds of problems other people couldn't get at because he'd worked out how to do calculus. So he was using his calculus to solve things, and then he would laboriously translate the final answer into terms that could be described as with geometry or algebra. So essentially erasing the evidence of having done it via calculus. Leibniz, on the other hand, discovers calculus and he goes, "Hey guys, look what I found!" And he started telling people about it. And as soon as he did, Newton was like, "No, I had that first. I did it like 20 years ago." Caused a big furor because like Leibniz was German and all the German math people got behind him, and Newton was English and all the English people got behind them, and it was like they were going to have a big math brawl. It didn't really go down that well, but it did cause a fair amount of rancor. There were people that were really upset about one person versus the other being the father of calculus. I suppose at this level we don't care. But he also did a lot of other stuff. Leibniz actually was interested in computers before computers even existed. He thought a lot about how to mechanize the ideas of thinking. In other words, he was sort of thinking about, could we produce mechanical brains? Now, it had to be mechanical back in those days because nobody had any idea about electricity yet. But you can do a lot of the same things with mechanisms that you can do with electrons. It's just way slower. If you have to wait for rods and levers to move, that takes a lot of time. Whereas you wait for a transistor to change state, it's in the femtoseconds. So yeah, you can do a lot more with a lot quicker things with modern electronics, but you could still kind of at least think about what should be the form of computing. So Leibniz did some of that work. And one of the things he did, what they're giving him credit for here in any case, is to visualize arguments. So when you say something like X is in the set of humans, implies X is in the set of mortals, in the all men are mortal sentence. You can picture that by essentially what's a Venn diagram. There is a set of humans and there's a set of mortals, and one is inside the other. I'm leaving a little gap so we can label them. Which is which? If you're saying, if you're human, you are necessarily mortal, it means that the humans lie all inside of the set of mortals. That is, you can think about implication as containment of one set and the other. If your humanity implies your mortality, that means the set of all human beings is inside the set of all things that have a finite lifespan. So that's one piece of it. That's the universal part. This is saying all humans are in here inside of the set of mortals. But then, where's the particular part? Well, the particular part on one of these diagrams is to take that particular person you were talking about, I believe it was Socrates, and put them down where they need to be. There's Socrates. He is a human being, so he belongs inside this set. And since this set is inside this bigger set, isn't it self-evident then that Socrates is immortal? I have to be careful about how I pronounce that. It sounded like I said Socrates is immortal. What I was trying to say was Socrates is a mortal. Right? So yeah, he's not immortal. He's inside the set of mortals. We had a similar setup for the modus tollens argument, where again you have the mortals and the humans entirely contained within that collection. You remember the prototype for modus tollens was about Zeus? Where does Zeus lie in this picture? He's certainly not human. He's not even mortal. He's not something with a finite lifespan. He's a god, so he's out here. But again, the containment is setting up a universally true thing, and then the placement of this particular thing leads us to go, well, if Zeus is outside the set of mortals, he most certainly is outside the set of humans, which is what Mo Stalin says. There's another take on the same thing that we saw in the previous section when we talked about arguments, the difference between soundness and validity. And so I think it's probably worth just banging this drum one more time. An argument is sound. Oh, sorry, let me say validity first. An argument is valid if its form is one of the recognized forms. Now, there are about 10 standard forms for these mini arguments, so-called syllogisms. An argument is valid if it fits one of those, if its form but, an argument can be valid and complete nonsense, as I think we saw in the worksheet 2 ago. You can have a valid argument that has a false major premise or has a false minor premise, and so the conclusion is not going to be valid. That issue, though, is really a separate thing. The form might be valid, but that doesn't mean that you're necessarily going to get a true conclusion. What else do you need to know? Well, you need to know the premises are all true. So that's what we call sound. An argument is sound in this sentence I was defining the word valid. Sound is being defined in this sentence, and it really means two things. It means the form has to be valid, and I want to emphasize that and because some people forget it. The other piece is you have to have valid or true premises. And so this, just in terms of how you think about stuff, this allows you to do some compartmentalizing. You can first analyze the form of the argument, say, okay, it's valid form. Now if I check up on the premises, I can tell you whether we can count on this conclusion being true. If you've got some questions about whether the premises are really true, and in the real world that happens. You look at a premise and you go, it seems okay, but I don't know. And people may debate it a little bit, and you go, all right, well then, maybe it's not true. If somebody can come up with a counterexample to when that premise being true, then you know that the rest of the argument is nonsense. I hate to, in the math world, it's usually really quite easy to check on something and see, is it true or is it false? But in real world, when we're arguing about politics or policies, and things can be matters of opinion. And people have strongly held opinions, but that doesn't make them correct. All right, so consider that horse to have been beaten to death, I guess. Validity versus soundness. We have the same kind of errors that we had when we talked about these things without quantifiers. So we'll have a converse error and an inverse error. They just look the same as they did before, but with the quantifiers thrown in. So if you had for all x, gotta remember to put in the universe, because I'm showing you bad form. If you had for all x, p of x implies q of x, and then q of x, let's not do x, it's supposed to be a particular thing, so p, and therefore p of p. That's just not right. How could we fix this? This is the converse error, and here's why. It's if you took the converse of the universal conditional sentence up front, you would end up with modus ponens. Let me just write that out because it's kind of important how you identify the errors. If we replaced the major premise with its converse, we would have modus ponens. So you think about what change you would need to make in order to get to modus ponens. Unfortunately, I've run out of room for writing ponens. So in this case, if you change the quantifier, change the order around in the major premise, the letters have changed. Now it would be Q implies P and Q therefore P, but that's the shape of a modus ponens argument. So that means, that tells you this one was the converse error. I can probably cheat a little bit and just make some changes to what I've written on this board to turn it into, to allow us to figure out what the inverse error is. Remember, in all of these things, whether they're the correct arguments or the converse or inverse error, the major premise remains the same. You start with, for all x in U, P of x implies Q of x. If I'm trying to do the inverse error, it would be the negation of P applied to P, and our conclusion would be the negation of Q applied to P. So that's no longer the converse, but rather the inverse error. Why? If we replace the major premise with its inverse, it would be modus ponens. This may be a little trickier to see. Let me just in red change this thing so that we get the inverse up there. Let's cross that out and say not P of x implies not Q of x. As changed, it's got the modus ponens form, because not P is the if, and it's also the minor premise. And not Q is the then, or the antecedent, and it's also the conclusion. So it's the shape of modus ponens with different letters, or with negated letters. Okay, we're kind of out here. There's one last subsection in this chapter about the hypothetical syllogism, or they call it universal transitivity here. But I think that we don't need it, because all of the argument forms that are on a handout, which you're going to get when we do a worksheet on this, all of them have versions where you just put quantifiers in front of everything, and you basically, it doesn't change the shape very much. It just turns them into universal arguments. Okay, so that's it for today. Let's see, it is 6 o'clock on Wednesday. I should have this posted because I've got to do some editing and time to upload it, but it should be up by relatively early this evening, maybe 7:30. So hopefully everybody will have a chance to look at it before class tomorrow. In case, I'll see you then, and have a good rest of your day.